now?
Yes.
Could you please proceed?
Yes, I will share my screen.
Thank you very much.
Just a second. Yes, so now we have to go into oops. I'm having a bit of a problem. Just a sec. Okay. Somehow it doesn't want to go into presentation mode. Okay, and everybody can see my presentation?
No, we can't see it.
No.
Okay, so this is a work about side. So this is a work about side channel analysis. Hello. So we worked on the CHESS 2018 challenge dataset. This was a side challenge, capture the flag challenge.
Sorry, we still can't see your screen.
You can't see my screen? I see. Okay. I did think I see. Okay. Sorry. This didn't. This doesn't. There should be no problem sharing one screen from the browser, should there? Doesn't seem to. Just a sec. Come on. Okay, we'll try it this way. Okay.
Yeah, it's there.
Can you see my screen now? Okay.
Yes, now we can see it.
Yeah. Sorry. But now you can't see it again. Oh dear. Can you see my screen?
No.
No.
Okay. I think this is a bit of an unforeseen problem. Doesn't show me the tab with my presentation, and it doesn't allow me to just share my whole screen. This is very annoying. Okay, I will try to do it with just the part of the screen. Can you see my screen now? It says that I should be that my screen should be shared now.
We see your screen, but we see you actually on the screen like this, so that this is your screen.
I can't. What did you say? I didn't understand you.
So we see. I would say we see your screen, but we see you on that screen, not your slides.
I see.
Or at least on one point, couple of seconds ago, I would say we saw your screen.
Okay, I will try again. Sorry. Now let's try this.
Aaron, one option would be that we schedule at the end of the session.
Yes,
if you want.
yes.
Probably
Maybe
better,
that's
right?
better. Yeah.
Okay.
Sorry. I will
Okay.
try to resolve the problem. Yeah.
You could also,
no worries. Go ahead.
if you share your slides with someone, someone else could go through it as well.
Yes, that would also be a possibility. Yes. Who shall I send the slides to?
Aaron, we will figure out later, and we will proceed to the next talk.
Yeah. Sorry. Yeah.
Yeah, no problem. No
I just.
So the second paper that we are going to present actually is going to be the first because of these technical problems. Is called correlation power analysis and higher order masking implementation of wage. Is the speaker here, please, for the second paper?
Yes, my name is Kalkinkar, so I'll present the paper. Just give me a second. So
Kalkinger will present from University of Waterloo. Is that right?
it's I recently moved to New Brunswick.
Okay.
So
Okay.
now, do you see my presentation?
Yes, perfectly.
Okay, great.
Go ahead, please.
Just 1 second. The displaying is fine, right? So far. Hello.
Yes, something happened. We don't see anything right now.
Yeah, you see my screen, right?
Yes.
Okay. Okay, great.
It's back.
Yes. Yes. So yeah, hello everyone. So I'm gonna present our work on the
We're
correlation.
just seeing a black screen though, Concur.
Oh, okay. So then I don't know. So now, how about now?
That looks
Now
good.
it's okay.
Okay. So
Now it's
now,
okay.
go. I won't make it a full screen. I'll just go this way to save time. Okay. So I'll present our work on correlation power analysis and higher order masking scheme of wage. So I'll make it short. So our contribution in this paper is twofold. So we first present the correlation power analysis on the wage algorithm, so which is a niche round 2 candidate, and then we propose a higher order countermeasure, which is this masking scheme for wage. So we know the side channel attacks are becoming more and more powerful day by day, and the power analysis is one of the technique. So from the power analysis, an adversary collects the power traces of a cryptographic algorithm, and from that adversary tries to recover a secret key. So here we are considering the correlation power analysis, which is one of the a type of the power analysis attacks. So and the solution for this power analysis is masking. So I'm gonna give some brief overview. So here basically, if we have a sensitive variable in the cryptographic algorithm, whatever sensitive variable we have, we just mask, we just hide. We don't keep the variable, we don't process that sensitive variable as a single value. We just create shares. So for n order sharing, so we share the value x, we denote it by double bracket, and we write it as x1, x2, xn. So now in this, if we share in this fashion, then XOR operation and NOT operation, these are very simple. But AND operation, it's a bit complex. So basically, because we are sharing it, so we need to compute this value x1, x2, xn product y1 plus y2, yn, because this is a huge overhead. So it has order of n square overhead. So now, and we prove when we are doing this computation, we need to prove that our computation is secure, right? So we will consider the probing model, and which is one of the popular model, where to provide tth order security, we need to have 2t plus 1, at least 2t plus 1 shares, and we will consider a strong non-interference security. So it's a very nice security model. So in this security notion, the number of share can be at least t plus 1. And another interesting property of this is it provides the composable. That means if we have multiple secure gadgets, then we can easily compose them. So now I'll give a brief overview of the wage algorithm. So this is a round 2 candidate in NIST. So wage is basically, it's a permutation based authenticated encryption, and the round function of the permutation is a Galois nonlinear feedback shift register. So it's a feedback shift register over GF2 to the 7, and there are total 6 S boxes in total, and 2 Welch-Gong permutation, we denoted by WGP, and there are 2 new S boxes. So now what we did, so we first analyze wage. So against power analysis. So wage is running in the device under test, this module. And there is a workstation which is basically providing nonce to the algorithm. And this oscilloscope is collecting the power traces, and a 3.3 volt is supplied. So this is how we are collecting 10,000 power traces for different nonces. And we are considering the initialization phase of the wage. So where we'll consider up to 12 rounds. For different nonce, we'll collect the different power traces, and we recover key in 2 phases. So in 2 batches. In the first batch, we recover 9 words, and in the second batch, 12 words. So because since wage works over F2 to the 7, that means each cell of the register is 7-bit. We divide the 128-bit key. The key is basically divided into those 19 register, where one register contains only 2 key bits. So in the first batch, we can recover these key bits. So here in the table, it's listed. So there are total 7 keywords, so which are listed. It can be, so these, for example, keyword 18 can be is recovered at round 10 from the state word 0. So here is an example of a power trace. So at the round 10, this is the power trace for recovering key 18. And then we apply the standard correlation power analysis, and we found that 246 is the leakiest time point, and each power trace contains 600 time points. And then after further analysis, we found that the key byte, the key which is integer representation is 96, it gives the highest correlation, and this is the correct key. So this is how we recover. And in the second batch recovery is a bit different. We cannot go any arbitrary order. We have to go in this following order. So because one keyword dependent on previous some other keywords. So that is how it is recovered. Then we saw this issue. Now we need to propose a countermeasure for this. So our goal is to provide propose a masking scheme which will provide TSNI security and which will be efficient for both hardware and software. So with this goal, so our idea is to share the state into n shares. And in the WGP algorithm, as I already shown in the figure, the WGP and S-box, these are 2 nonlinear operations, and rest of operations are linear, and they can be done easily. But the most complex part is WGP and SB. So our contribution here is we present an efficient implementation for this WGP, which is we denote by secure WGP and secure SB. So this is a diagram for a 2-share for a 2-share states, and it provides the first order security. We see these FB computation and shift register operation can be done parallelly. Only the cross shares needs to be involved in this secure WGP and SB computation. And so this is an algorithmic description. We won't go into detail, but here I want to emphasize some of the optimizations for the secure WGP. So we produced a circuit for the WGP, which containing 172 AND gates and 313 XOR gates and 66 NOT gates. And here our idea is to replace each AND gate by a TSNI secure AND gate. And this Barthe et al. Already proved that if we can compose them securely, it provides the secure WGP provides TSNI security. Similarly, the S-box construction is iterative and it's a quadratic function. And so our main observation is that we see there are 2 common terms. So here we apply a common multiplication sharing, which is proposed by the Coron et al. We apply it and we see, and we implemented, see, for example, for n equal to 4 shares, we are saving 21 gate equivalent. So with these optimizations, we proposed a secure S-box construction. And then I won't go into the security details, but I want to give an example here. For example, for first order sharing case, we need about 56,610 bits, random bits, to protect wedge. And we implemented this wedge AEAD scheme in 2 different ASIC libraries, ST micro and TSMC.
One more minute, please.
Yes, I'll finish it soon. So the first order needs about the 11.12 kilogate, and the third order, for example, 33.98 kilogates. And we also compared with the state-of-art other lightweight crypto algorithms. So wedge still has the better hardware area. And so that's all. Thank you. I'm happy to take questions in the Q&A session.
Okay, thank you very much, Calendar. We are leaving the questions by the end of this session, that we will have all the discussion about these 4 papers. And for now, we move to the 3rd paper of this session, which is on the influence of optimizers in deep learning-based side channel analysis, that is going to present by Stefan. Could you please proceed, Stefan?
Yes. So hopefully you can see my screen now.
We do.
Excellent. So thank you all for listening for this talk. So the title is On the Influence of Optimizers in Deep Learning-Based Side Channel Analysis. The author is my postdoc Guilherme Perin and me, Stepan. Unfortunately, Guilherme cannot join today, so I was selected to present the paper. So what's the point of this paper? Like already said, side channel, we know that especially with machine learning today, we can get very, very powerful attacks. And from one side, we are exploring different architectures. So we are getting either to more and bigger or deeper and deeper architectures, or from the other side, we are exploring very small architectures, both capable of delivering extremely good results, extremely good attack performance. But at the same time, there are a number of hyperparameters of those neural networks that we kind of take for granted, and we don't really explore what's the influence of those hyperparameters on the end behavior for the attack. And that's the motivation for this paper. We wanted to explore the role of different optimizers in side channel attack performance. So basically, we divided the optimizers into two categories, adaptive and stochastic gradient descent based. And we tested behavior for multi-layer perceptrons and convolutional neural networks on different data sets. We also kind of ad hoc do a, let's say, division into small and large neural network models. So having many or relatively small number of trainable parameters to see the influence. So since the talk is very short, I will skip this deep learning based profiling side channel attack, where we have one device where we do the profiling. So we build the model, and then we have the other device that we really attack. And then we go for the effort, going from the pre-processing efforts in side channel that are almost now with deep learning regarded as not needed, towards hyperparameter tuning effort that is now considered as the main effort to train a good neural network. And as such, knowledge about specific hyperparameters is important. And then you can do various types. How do you want to search for good options of hyperparameters? But of course, the more options you have, the more testing you need to do to find strong architectures. So how long do we want to train our neural network? Well, depends, for instance, on the type of the optimizer. Here you can see one result for RMS prop, the other result for SGD. And that tells us, well, we can also consider the performance from the regularization perspective. So do we want to do implicit regularization and have less overfitting, or do we want to have explicit regularization where we fight against overfitting, and so on and so on. So what are optimizers? To answer the main question here. Well, optimizers define how we update the equation according to loss function and learning rate. So here you can see equation, and optimizers will tell us, well, how do we update this equation to obtain as good as possible neural network parameters. And these are the settings that we tested. So these are the optimizers we explored: adaptive, ADAM, RMS prop, ADAGRAD, and ADA delta. And from the SGD family, SGD, SGD plus momentum, SGD Nesterov, SGD Nesterov plus momentum. So once the typical attack, well, successful attack, we see a picture like this. So we measure guessing entropy that decreases as with the number of epochs increasing, or with the number of attack traces increasing. But unfortunately, we can also see behavior like this, where you can see that the end result is actually worse than at some middle point, because we overfitted and we do not know how to generalize to unseen data. So this is the point here called early stopping, where we would like to stop the training. And this is also the point where we want to regularize to get that behavior. So what do we attack? We attack ASCII fixed keys and ASCII random keys data sets, like the name says, either fixed key for training and test set, or random keys in the training set. And here you can see a little bit on the methodology. So what kind of architectures do we really test? And now some results. I'm basically skipping over the results, because each of those figures we could discuss for 10 minutes. What do we see? But we see here for different data sets, two dominant behaviors. So we either see behavior where the guessing entropy slowly decreases with the number of epochs, or we get extremely quick decrease of guessing entropy, but then as the number of epochs start to grow, we actually see slight decrease in the attack performance. So this would be for Adam, Adagrad, RMS prop, and Ada delta, and similar type of behavior again for SGD type of optimizers. So this already tells us, okay, depending how we select the optimizer, maybe we should stop the training extremely fast, or we should leave it for a very, very long time. And it also depends, of course, on the size of our neural network. So here you can see some more results for small MLP, for small CNN, and then results for large MLPs and large CNNs. For both, of course, SGD and Adam type of optimizers. Like I said, I really go through results quickly. In the discussion, we can discuss anything. What is also important to note here in this paper, well, in this work, we also observed a behavior called deep double descent. So it's a behavior when you improve, then start to degrade, and then you again start to improve. So this is what we show here. So you have large model or intermediate model size or small model size, and you see this knee where the behaviors goes towards worse and then again towards better. And actually, this is what we also observed with side channel. So here you can see the green color where the performance around 100 epochs goes to very good guessing entropy, then it decreases to relatively bad guessing entropy, and then again after 200 epochs, it improves again. So we actually showed that this deep double descent behavior does happen also in side channel, which is very important because it tells us the bigger is not always the better. So longer training is not always the better. Larger models are not always the better. To conclude, we showed that Adam and RMS prop easily overfit. Why is this important? Because those two optimizers are commonly used in side channel. And then we see that the training either needs to be short or combined with explicit regularization. On the other hand, we showed that Adagrad actually shows very good performance if we use large models and large training phases. SGD provides less overfitting, but it's quite slow to converge. And like I already said, more is not always better because we can get deep double descent in side channel analysis also. But of course, small models also work relatively well. And thank you. And for any questions, yeah, like I said, we will have the discussion phase in the end.
Thank you, Stefan, for the nice presentation. Yes, we will have the discussion phase, and we can ask you questions then. For now, we are going to move to our fourth scheduled paper for this session and the last one, but we are going to make up for the first one where we have some technical problems. So this paper that we are going to present right now is high throughput elliptic curve cryptography using AVX2 vector instructions. Could the speaker please take over? Is the speaker here for?
Yeah, everybody. Yeah. I will present paper now. Excuse me, can you see my screen?
Yep.
We can see it.
Okay, thank you. Hello, everybody. I'm Hao. So I will present our paper entitled High Throughput Elliptic Curve Cryptography using AVX2 vector instructions. This is a joint work with Johan, Jiaqi, Peter, and Peter. Currently, all the existing implementation of X25519 optimized with AVX vector instructions are minimizing the latency of single-scale multiplication. But the benchmarking result published in the literature showed the parallel implementation of scale multiplication do not scale very well when switching one generation of the AVX to the next. For example, AVX 512 doubles the amount of parallelism compared to AVX 2, but the latency reduction is only about 25%. So this immediately raises question that how implementers can exploit the massive parallelism of future SIMD extensions in ECC. And going along with this how question is why question. That is, why are fast implementations needed? Or put differently, what applications demand low latency implementations? But unfortunately, none of those papers identify a use case for their low latency implementation. Since many security protocols nowadays support X25519, for example, TLS 1.3, so one may argue that a latency optimized implementation will reduce the overall handshake latency for a TLS client side. But the problem with this reasoning is that transmitting the public keys over the internet will most likely introduce orders of magnitude higher latency than the computation of the shared secret. Given the clock frequency of 4 GHz, a user will most likely not recognize the time reduction by a few 10,000 clock cycles. So it could be now argued that scale modification is not only needed on the client side, but also to be performed by the TLS server. Indeed, the TLS servers of big organizations like Google or Facebook may be confronted with several 10,000 TLS handshakes per second. And a faster scale modification will help them to cope with such extreme workload. But what really counts on the server side is not the latency of a single scale modification, but the throughput. That is how many scale modifications computed per second. So in this work, we introduce a throughput optimized AVX2 implementation of X25519, and we will see what throughput it can achieve compared to the latency optimized implementations. So our method is actually kind of simple, that we perform 4 scale modifications simultaneously in a SIMD fashion. And each instance is independent of each other, and each one uses 64-bit element of 256-bit AVX2 vector. So our method has several advantages. First, it's very easy to implement. We can basically just simply vectorize the reduced radix implementation of X25519. And second, because each instance is independent of each other, so in this way, we can fully exploit parallelism of the SIMD extensions. And third, our method supports various SIMD extensions, not only the AVX2. For example, there is straightforward extension to AVX512 that to perform 8 scale modifications in parallel. And in theory, we suppose that our method scales better than optimizing for the low latency. For example, when switching from AVX2 to AVX512. So other details, we employ the radix 2229 representation for the field element. And we develop a dozen of candidates for the field multiplication. And from the benchmark, we obtain the fastest one. The distinctions of these candidates are shown here. And in addition, for the point operations, we observe that our software does not require each subtraction to perform the carry propagation and model reduction. So if we use ordinary subtraction properly, the overall performance will get improved by around 5%. Okay, to compare with the state-of-the-art latency optimized AVX2 implementation on Haswell, our implementation increases the throughput of the key generation for around 60% and increase throughput of the shared secret for 45%. And on Skylake, our software has 70% more throughput for the key generation and 50% more for the shared secret. To summarize our work finds that AVX2 offers great potential to optimize ECC, and all the existing implementation use AVX2 to minimize a latency of single scale modification. Our work is the first to use AVX2 to maximize the throughput. And our implementation has 1.5 times to 1.7 times throughput compared to the state of the art. There exists a straightforward extension to AVX512, which in theory doubled throughput. Okay, that's it. Thank you for your attention and welcome to have a look at our source code.
Thank you, Hal, for your nice presentation. We are now ready to try again the first paper. So,
yes, thank you. I will try once to share my screen. If that doesn't work, then Michael has my slides. So we'll just try this very quickly if this works now. Can everybody see my screen? My slides?
Yes, we can. Yes, we can.
Very good. So this is a work about side channel analysis, and we worked on the CHESS 2018 challenge data set. this is a data set on a masked AES software implementation during the contest. No details on the masking scheme were released by the organizers. The challenge task was to recover the key from 1,000 traces. There were two parts of the challenge. One was a challenge with 1,000 traces for a device that was already in the training data set. Then there was 1,000 traces for an unknown device. And this was the harder, more interesting part of the challenge. We show in this work how we can do this fairly reliably. This is roughly a 70% expected success rate on the unknown device challenge using just a single power trace. And we also introduce a new method for leakage attribution. And our code is available on GitHub. So our basic attack design is it's a two-step attack. We have, in the first phase of the attack, we predict the Hamming weights of the expanded AES key. So the 10-round AES has 11 subkeys. Each subkey has 16 bytes. So in total, we have 176 subkey bytes. And we try to predict the Hamming weights of these subkey bytes based on the trace using machine learning. Then in the second phase, we use a subsolver to find the key. In the paper, we present three different methods for phase one. First, there are two linear predictors, which we call baseline and up, and one deep neural network. The deep neural network uses a very scalable novel architecture for neural network-based side channel analysis. And the up predictor, and especially the deep neural network, outperform all previous solutions. So with subsolvers, this is plan. This is attack plan. One has the problem, of course, that subsolvers are not known to be tolerant of mistakes. So if we have some constraints on the Hamming weights, and if any of these 176 constraints turns out to be wrong, then our subsolver will work for some time and it will return, I can't solve this. And so in order to avoid this situation, we use a tried and true principle of avoiding errors in predictions by making sufficiently vague predictions first. So this means we give the subsolver only a top two guess. So we guess its Hamming weight is one of two values. And secondly, since this isn't enough to avoid all errors, we randomly drop some of our constraints and try again if our subsolver is unsuccessful. And this method gives us a fairly good success rate. So this is the number of cases in which the different predictors that we consider predict the Hamming weights with less than 4 top 2 errors, which is the most that our error correction method can handle. So we see that the deep neural network has roughly a 76% success rate under this metric. The up predictor, which is trained entirely on adversarial examples for our deep neural network, so it is trained on kind of invented data and not on the original training data. It also has still a fairly good success rate, even in the single trace setting. The baseline predictor is just a linear predictor that is trained on the original data, but otherwise identical to the up predictor. And SAC2020 is a template attack that was developed by Freud and Klein, and which also solves the RAS challenge. So in conclusion, a combination of a deep neural network, a modern subsolver, and a simple error correcting scheme can very efficiently break the CHESS 2018 RAS challenge. And adversarial examples, which we used to derive the up predictor, can be a useful tool for transferring knowledge from our deep neural network to a linear predictor, because this predictor that was trained entirely on invented examples outperforms quite significantly an equivalent linear predictor that is trained on the original training data set. And finally, we reused our neural network architecture with some significant additional ideas, also to break all software challenges of the CHESS Challenge 2020. And with that, I'm finished. Thank you.
Thank you, Aaron. It's nice that you could present your the talk as intended first. Okay, we are now going to move to the phase session, to the discussion of phase session phase. So we have already several questions that I will read right now. So for the paper on the influence of optimizer for Stefan, we have this question from Colin. Colin asked, you have the note in the paper about trying these on 2 data sets. Based on your findings so far, do you end up with a set of good reasonable default settings? A researcher can somewhat blindly start with and expect reasonably good results? That's a question by